So in this illustration, I will try to demonstrate to you internet load balancing for egress traffic. And the way this design achieves that is by using two features called MLAG and VARP. And MLAG is multi-chassis link aggregation. In Cisco terms, it's VPC. In Arista terms, it's MLAG. Essentially, these two switches become one switch, virtual switch, for the device that's connecting to them. So in my case, I've got a Fortigate firewall with port 2 and port 3 Portchannels connected to switch 1, Arista switch 1, Arista switch 2 in a MLAG fashion, so that for firewall it appears it's connected to a single switch. And if this link fails, it automatically fails over to this one. In fact, it load balances on both. So if you put this design into an ISP egress deployment, it would actually take your traffic from users and load balance for the egress ISP or internet traffic. Now on the switches, Arista switches, I've emulated ISP connection through loopback. So each switch has a loopback, 100, 111 connected or configured. So there are no two ISPs. I'm just emulating that they are connected to an ISP on both sides. So they are configured with loopback. This guy, VOS 2 and 3 are going to be pinging and trying to reach 100, 111. We'll do a failover for firewall and see how that does. And without failover, we'll also see how it actually does a load balancing. So what we are not using in this topology is a protocol which is kind of popular with Cisco topologies, and that is called HSRP or VRRP. And what is the advantage or disadvantage of doing VRRP / HSRP versus VARP? Well, so the VARP is a Arista technology or feature. It is available in Cisco, but not across the board. What it does virtual ARP. So with HSRP and a VRRP, your hellos or control traffic will traverse the peer link. With VARP, all you got to do is configure this on the interfaces that you want the VARP on, or the subnets that you want the VARP on. In our case, it's 2400. And then it's only gonna send ARP responses on this one. So in VARP, this link is not used. It's not used. It's not used. This link is only dedicated for MLAG purposes and nothing else. The other thing with VRP or HSRP is each group that you configure, it's always in active standby. So you have an active and you have a standby, and then for load balancing, you're going to have to configure for each single VLAN as separate active. So one VLAN is active here, the other other VLAN is going to be active here, and this one is standby for the other VLAN, and so on and so forth, just to do load balancing. So that's a lot of configuration. It makes it complex if you want to do load balancing with this guy. And then on the top of that, you're going to have to configure some tracking objects to configure this link. You configure this link to be tracked so that it fails. Inherently or natively, HSRP VRP was designed for system failures. So if this guy fails, this one becomes the active instead of standby. But if you're tracking link failures, then you have to create tracking objects, and I'll put up a video on that too. So now we're using the Arista VARP, which get rid of this guy, get rid of this guy, doesn't use this guy, and no need for active standby. So it is a very, very clean solution and a very simple solution that would give you failover as well as load balancing with MLAG and this feature here. So again, I'm using Arista virtual switches here. I have a FortiGate load firewall with Portchannel configured on it, and it would automatically load balance / failover. Now let's take a look at this configuration. So I've got a VLAN 10 configured on both the switches with a very simple command, virtual router, and then a virtual MAC address. Therefore, and the firewall is connected with port 2 and 3 in a Portchannel fashion. So I'll start giving you the configuration snapshots. This is my firewall. I'm gonna log into this guy. Make sure it's completely visible. So in the firewall, it's pretty straightforward. Let's see if I can make this fit. Firewall is configured with the Portchannel, and Portchannel has VLAN 10 with an IP address of 24001. Now, Portchannel, when you want to configure a Portchannel, you simply go create interface, and then you just say the type is aggregate, and then you add your interfaces. In my case, 2 and 3 are already added to this. So I'll show you that Portchannel configuration. 802.3 AD aggregation protocol type. It's a Portchannel, port 2 and 3s. 3 are added to this as a member, and there is no IP address configured on it. Okay. What I also did is created another interface called interface VLAN type, and then added VLAN 10 here, which is part of Portchannel. So here's my VLAN 10, and that's your DMZ VLAN in this case. And its IP address is 24001. Nothing special here. It's configured with interface Portchannel 1. And that's about it. What I've done is I've got static routes pointing to towards my source. In fact, I don't even need these because I'm doing a NAT. So all of this is pretty much in my actual scenario not required, but you need a default route towards ISP, and if you're not doing that, then static routes towards your corporate network. So here's your firewall that we just looked at, the configuration with Portchannel and NAT. So NAT is going to be using 24001 to go out. I have no routing configured. So if I am bringing my source as 10, then I can disable NAT and configure out routing here with switches to go back to the firewall. But in reality, in the real world, you'll probably have a NAT. Your 10.network would be behind the firewall. Now again, one note on active firewalls is that it's a complex design and not very easy to deploy because it's got issues with VPN and IPsec. If you have active, this firewall needs to be in sync with state. That means you need to have a big firewall. And then number two, if you're coming in a VPN on this device and your load balancing is going this way, then your VPN is going to break or IPsec is going to break for any application. So it's a lot more complicated, very specific use cases if you're using firewalls, active. Here we are using one active firewall. You can configure this with an HA, but it's going to be connected to the egress or edge devices, whether a router or switch. In this case, it's a switch. So now the latency also, so just to make sure that I illustrate the latency part so that we have a good visual of it, is this portion is, this link is configured with latency 200. And this link is configured with 500. So by default, the firewall is going to send it here. And then just for the pings, you'll see that. And when we failover, it's going to failover to this link, and you'll see turns to 500. So let's do that. That's my VOS 2. This one right here, and I'm going to be pinging this guy. Show interface is already visible. This one is .2. So I'm going to ping. So now you can see the latency is 200, and it's taking this path. And this guy, VOS 3, is the firewall is going to redirect it here too for the pings. You can see both of them are taking this single link. Now again, this is just for the ping, but if you do a telnet, an actual session, so if you are initiating a session towards the internet, you would see that the firewall will actually load balance. So I've configured switch 1. Actually, this is switch 2 and this is switch 4. So let me kind of fix that picture. This is actually switch 2, and this is switch 4. Beautiful. Switch 4. Now this is my switch 2 and this is my switch 4. Now let's take a look at the telnets. So I would do telnet. Again, my loop 100.111 is configured as a loopback interface on the switch 2 and switch 4. Telnet 100. So this is going to switch 2. Do it one more time. There you go, it goes to switch 4. So that just tells you right there that it's actually load balancing for TCP sessions, for any sessions that are connection oriented. It's actually load balancing. Switch 2, and then it went to switch 4. Same thing with this guy. Switch 2, switch 2, switch 4. So your firewall by default is load balancing the sessions. It's just not load balancing the pings. All right, so that's your load balancing part. So it's actually going like this, right? Switch 2 and switch 4. So it's taking your internet exits and it's load balancing with this VARP feature. Now let's let's do the failover test. So I'm pinging and it's taking 200 milliseconds, which basically means it's going through this link. So it's taking 200 from both sides. Basically for the pings, it's sending everything here. So that's good. We'll see as soon as we failover this link, port 2, keep an eye on these. 200 will change into 500. So let's failover our port 2, which is adapter 3. No, it's adapter 2. Port 1, port 2 is adapter 2. Okay, so we're going to fail over this guy. And let's see what happens. Failover, right away switch to 500. Not a single drop. So that's the advantage of your port channeling. And it's not taking this link anymore. It's going through this link. And there is nothing, no VRP configured on the switches. It's only VARP. I'll show you the configs for the VARP. It's just pretty much 2 commands. Let's reconnect or link. Port 2 connected. And it'll fall back to its original port right there. Same here. So you can see it was load balancing a session and pretty much preferring ICMP through one port. I think there may be a way to load balancing ICMP as well. This is very Fortigate specific, but again, port channeling configured on Fortinet firewall, and it is using your switches, edge switches / L3 devices is using MLAG with VARP. So what's your VARP configuration looking like? Show run interface VLAN 10. Show run interface VLAN 10. Both sides have a virtual router address 240010, which is the default gateway for your firewall. Firewall is pointing towards this address. The actual address is .4, .2, but the VARP address is 240010. That's the address the firewall is reaching. And whoever responses with an ARP, which both of them are actively, it'll go to that device. Show, you just need one more command to activate VARP, and that is this guy, IP virtual router MAC address. You configure the MAC address on both switches. Here it is. IP virtual MAC address, IP virtual router address on the interface on the global command. And that's your VARP. That's it. No, and it load balances. So it's pretty neat how it does it. So here's your MLAG. MLAG is very straightforward as well. It requires an IP address and a VLAN 4094. I just looked at the Arista documentation, and that's how you configure it on both sides for the MLAG, and that's it. Your MLAG comes up. You can verify MLAG by saying show MLAG, and it'll tell you that it's consistent, active, and connected. So this design, in my opinion, if you think otherwise, let me know, is much more neater, cleaner, simple, elegant, with load balancing, with minimal config. Again, compared to VRP, which uses your peer link for your control traffic and then act as standby for each group is quite a bit. So I think this is a much smoother and nicer, cleaner design for an ISP egress, or for that matter, if you have a host. I'll put up another video, but if you have a host, pretend that you have a host instead of firewall, and your access layer. This is your access layer right here. So instead of an edge, this is your access layer. And this guy is your host. So host will have two NICs, and you'll configure those two NICs. That's how typically a data center is, with host having two NICs or more configured in a port channel, your access layer, and you have this configured instead of VRP. Instead of VRP, HSRP, you do MLAG, because VRP, MLAG would work with either VRP, HSRP, or VARP. So here, you can configure your access layer, which is going to be an L3, obviously, your default gateway. L3 means your default gateway from your host would be your first hop, your L3 switch. In a traditional design, I have that spine leaf architecture where your typical design, your access layer is an L2 instead of an L3. But this could be a host, and you'll achieve the same thing with the host configuring to an access layer, which you can put the same design in ISP egress load balancing with MLAG and VARP. Hope this helps.